Welcome also from my side, and I'm pretty sure everybody in here occasionally experiences some pain in the joints, especially if you think of your knees. In most of the cases, this pain goes away with time, but in more severe cases, the pain becomes chronic and requires medical treatment. And you can imagine joint diseases are quite widespread, especially if you think of elderly people. And the amounts spent on the treatment of joint diseases is huge. That's a huge amount for the health system. And due to the importance of this topic, we called in the Saints, Enhancing Arthritis with Integrated Novel Tools. It's a LIT seed project. Thomas Vogelhuber is the project manager, and the goal is to apply for more research money and to get in touch with more partners. So what is our approach? So one important component of each joint is the liquid, the synovial fluid that ensures proper lubrication and nutrition of the cartilage. So our focus is definitely the analysis of the synovial fluid. And the idea is to have a tool that can be used at the point of care, so at the doctor that does the examination, to have an early diagnosis of joint diseases and to also a therapy tracking of the medication. The joint liquid is actually more a hydrogel, as Martin mentioned before. It has a complex composition and is really very far away from what technical lubricants look like. And usually it's a clear liquid with elastic properties, but in some cases it can contain particulate matter like the cartilage wear, cells, or gout crystals. So gout is a disease where crystals form within the joint liquid and can lead to inflammations. The fluid, as I mentioned, is a complex composite material. It's viscoelastic, so it has both the properties of a liquid, so it flows, and an elastic solid, so you can stretch it to a certain amount. And what is responsible for this property is the component hyaluronic acid, which there is present in high molecular weights and which has a complex interplay with proteins to give the synovial fluid the exact properties it needs for its physiological function. So here is a picture of the knee joint. One important part, if you want to do diagnosis on the joint liquid, of course you have to get it out of the joint, and this is done with just a needle, but it's a rather standard procedure, more comparable to take blood for analysis. And on the right-hand side, you have a polarized light microscopy image of gout crystals that consist of urate crystals. So our approach is to have a combination of joint aspiration, so so withdraw liquid from the joint, and you can combine it with the overall medical condition of the patient and our sensor data to determine the physiological state. In the standard procedure done today, the joint liquid is sent to the laboratory, and you have to wait a certain amount of time, usually weeks, until you get a complete diagnosis. And with our approach, the goal is to do as much as possible at the point of care so that the doctor can tell immediately what is wrong and which kind of treatment is necessary. As we are not coming from biology, we are not focusing on the biomolecular part of the analysis, but more concentrate on the physical properties of the joint liquid. And this is the viscoelastic property, density, and yeah, things like that. So our target parameters are the concentration and molecular weight of the hyaluronic acid. The reference methods we use in internal corporations at JKU is gel permeation chromatography and microreology. Yeah, and of course, as mentioned before, the goal is to quantify the particular matter. The technical solutions that came into our mind is acoustic steering microbalance. So these are the three approaches I will present during the rest of my talk. The second is the monitoring of sodium urate crystallization, not only to prove that we can detect the crystals, but also to analyze the tendency of the fluid to form urate crystals. And this is something really novel because usually if you just withdraw the joint liquid and look at it, you only can determine are there crystals or not. And with our method, we could in principle detect what is the tendency of the liquid to form these crystals at all. And finally, I present a method which tests the elastic property of the liquid by doing a highly nonlinear stretching of the fluid with an electric field. So first is the acoustic steering microbalance. It consists of the combination of a low-frequency electrodynamic resonator with a quartz crystal microbalance. So the quartz crystal microbalance, maybe some of you know this principle. It's used quite often in biology and in the fabrication of semiconductors to weigh thin layers of mass. And we combine these two methods in order to have an acoustic steering effect. So the low frequency resonance is at around 240 Hertz, and it's an out-of-plane motion of this platelet. And the quartz crystal microbalance works in a way that the quartz disk does a bulk oscillation and also has an internal resonance. Yeah, just to mention here, this resonance behavior is measured using a device fabricated by a spin-off company at our institute called Microresonant. So here's an image of the acoustic streaming effect. We have this plate here, which is moved as a whole by the low-frequency actuation. This leads to capillary waves on the surface of the droplet and consecutively produces an internal streaming effect. Yeah, the idea to measure the particulate matter content is to do a repeated steering of the droplet and then a combination with the microbalance or measuring the resonance of the low-frequency resonance and observe the settling behavior of particles. So if we steer it up, the particles are completely suspended, and then if we stop the steering, we can wait if there is sedimentation, and this sedimentation process we detect with the microbalance. So here's a high-speed video of the actuation mechanisms. Here we see these capillary waves, and the internal streaming is not quite visible here, but we put in here tracer particles to observe the streaming velocity, and it is quite high, so the suspension of these particles is facilitated pretty well. And here is the repeated steering and settling experiment. So we have periods of steering and then the periods of settling where the mass of the plate increases and which decreases the resonance frequency. In a similar manner, the quality effect of the resonance is influenced. So this was our first approach. The second is the detection of sodium urate crystals in the liquid. And for this, we again use a resonant principle to measure viscosity and density at the same time during the process of nucleation of crystals in the liquid. So we have here a sample liquid with the prepared chemicals in there. So at the moment for this experiment, we are not using synovial fluid, but artificial solutions which just have the right ingredients to form crystals. And we can use this sensor to measure the nucleation stages of crystallization over long periods. So we have the Q factor of the resonance. It's again a resonator which has the shape of a tuning fork and is actuated in a piezoelectric way. And the Q factor is related to the viscosity, so decreasing the Q factor means increasing viscosity. And this comes from the fact that from the initial completely liquid, homogeneous state, crystallites form, and these crystals increase the viscosity because there are particles now interacting with each other or with the liquid. So after a certain time of nucleation and the viscosity increase, it settles to a steady value, and this is because the crystallites become large enough to settle to the bottom where they are not anymore detected by the sensor. Yeah, and again we can use a kind of similar experiment as before. We use a stir-up and observe the sedimentation process to detect and quantify the particles. And the last method is based on an effect that an electric field is used to apply a force to the liquid droplet. And there's a laboratory method that is occasionally used in rheology where there's just two plates, as a liquid is filled between two plates and then suddenly stretched, and the thin filament is formed, and the breakup of this filament is monitored to measure the properties of elasticity of the liquid. In our approach, we don't use mechanically moving plates, but we use the liquid directly from the syringe tip, put it in an isolating oil, so it's silicone oil, which has both the effect of electrical isolation, because we use pretty high voltages here, and the other effect is that the synovial fluid is not really stable in contact with air. So with the immersion in the oil, we prevent the formation of a thin layer at the outer interface of the droplet. So if you apply here an electric voltage over the tip needle and the ground electrode, a filament is formed by the electrostatic forces acting on the droplet. So this is shown here on the right side. Here is a continuous filament from the top needle to the bottom. You can imagine that if you do this with a water droplet, the droplet will pretty soon break up and you don't have this filament. Even if you use artificial hydrogels like alginate, which has a comparable molecular weight as the hyaluronic acid in the synovia, you cannot really form a large filament. But with a healthy synovia, like in this case, it is possible to draw a large filament. So here is the visualization of this process. At the top, you see a high-speed imaging with a real synovia sample. And at the bottom is a pretty time-consuming simulation of this process. There's still some work needs to be done because this is pretty low elasticity for the liquid. But if in the simulation I want to simulate an elastic fluid, the simulation pretty soon does not converge anymore. So it's a numerically ill-posed problem. All right, so this is the end of my talk. Let me sum up. We are aiming at a microsensor platform for biofluid analysis. We especially look at the viscoelasticity and particulate matter content in synovial fluids. At the moment, we performed experiments with artificial fluids and with canine synovia that was supplied by the University of Gießen. We're doing reference experiments with two institutes of JKU, Institute for Polymer Science and Institute for Chemical Technology of Organic Materials. We believe that these methods are potentially useful for other biofluids as well, and probably for the diagnosis of different diseases. And we had initial contacts with medical staff from Kepler University Clinic, and in later stages of the project we will pursue experiments with human samples. Okay, thanks for your attention.